Please go ahead.
Sure. Hey, everyone. Great to be here to share our research about type inference. My name is Xu, and it's a joint work with my great mates Chen and Shengyi. Chen is also present in the audiences, and our supervisor, Bruno Oliveira. We all come from University of Hong Kong. Let me begin with the first demystifying the title, since it's relatively short. Local Contextual Type Inference, locally simple, because we are presenting a local algorithms. Contextual basically means, it's from my previous work called the contextual typing, which is a conceptual idea that generalizes over the bidirectional typing. And there's also a term hidden inside called the local type inference. And it implies two different angles to view our work. The first is this work is a direct extension of the contextual typing by applying its conceptual ideas to the polymorphic type systems. The second, this work can be viewed as a refinement of the local type inference by providing alternative but simpler specification and also removing some practical restrictions. I will cover two backgrounds first, and then we go to the main systems. Local type inference has been proposed by Pierce and Turner in about 2 decades ago. It's widely adopted by mainly practical languages, including the Java, Scala, C#, and TypeScript. It's considered as the partial type inference method, which means when programmed with a language that using local type inference, you are required to put a certain amount of type annotations to trigger or guide the type inference and type checking, which makes it scale to advanced features, including the implicit, impredictive instantiation, and also the subtyping. Local type inference consists of 2 key ideas. The first is the bidirectional typing to allow the type information to be propagated from one node to its labeling node in the syntax tree. The second is, of course, the local synthesis of type arguments to allow you to write polymorphic function application without explicitly writing down a type argument. To my view, the local type inference is very successful, but there are still some places we can make even better. As you can see, below are the 2 function application rules for the local type inference. The first deals with function application with explicit type argument. The second deals with implicit polymorphism. As you can see, their functions are default uncurried and whose types are merged with polymorphic types, which make it farther away from the standard system like systemf. And it has 4 application rules, whose instantiation logic is monomorphic, which makes the new researchers too hard to understand and extend. The third is their locality is limited to an argument of an uncurried application, makes it cannot propagate from the information from one argument list to another one. It's mainly due to by the rule, it requires all the arguments in the list to be all inferable, which is very different from how practical languages behaves, because in practical languages like Java, it uses the instantiation information immediately in a left-to-right order, which means if you learn some type information from one argument, then you can use this type information to immediately to type check the next argument. Okay, great. Let's bring up to the second background. What's contextual typing? Let's think of a scenario. Suppose you are designing a bidirectional type system. For function application rules, you will face 2 choices. The first to inferring the type of function first, and the check against the arguments, which gives the rule like this. And second option is the reverse. You first infer the type of argument, then you partial inferring the type of functions. What's the partial inferring? Because the E1, the function E1, only knows the partial information, which is type A here. And we have no good specification for this. The first direction is great. It's a default choice for many languages, and it's very useful for the high order application. The second one is we have non-suitable modes for the function, so I use a red question mark here, but it's still very useful for especially for the type inference with polymorphic function instantiation, where you wish to use the argument information to assist the inference of functions. And if you are even more ambitious, you want both in your system. You got the second trouble, which is backtracking, because two rules are just a syntax direct overlapped. Contextual typing is a work from 2 years ago that gives the solutions to two troubles. The first is how to find a way to specify the partial inference. It introduced so-called the contextual type assignment system, so-called the CTAs, that encourages do not use the modes, use the masks. What is masks really? In syntax, it's simple. It's just a sequence of two kinds of boxes. We have the transparent box and opaque box. Then you can decorate your typing judgment using the emph, which is a mask. The masks characterize what information we know from the context. Let's try some examples. If we have an opaque one, which means we see nothing in the context, and we use red color A here to indicate A is fully unknown. If the mask is a transparent one, we see everything in the context. We use blue color to indicate A is fully known. What if the mask is a sequence, then transparent, then opaque, which indicates the partial that input type A is known, but B is unknown. Then we can write the application rule in this way. You first analyze the argument and it type checks with a mask A, and we further propagate this information to the context to the mask of E1, the function part, by prepending this one to the M. Then E1 is aware of more information. So the intuition is you can understand the application rules works as the mask collectors. It collects more and more contextual information, and it can do more things. So the second trouble is backtracking. Our principle is in algorithm, do not decide the inference and checking of arguments in application. Decide it when it's consumed. I will not explain what's the notion of consume here. You can read the paper. But the key idea is that we introduce so-called the contexts, use sigma, and to store the deferred type checking tasks of the arguments. Here's the rule for the function application. You can see we have the context. We wish to infer a function application E1 applied to E2. We do nothing about the argument, but only prepend this argument to the syntax for the E1. So E1 is aware of more context, and they will analyze this information later. In the end, the two systems are proved to be equivalent. The specification using the masks, the algorithm using the contexts. And great, we are now equipped with enough knowledge to understand what's the local contextual type inference. It's a refinement of local type inference by using the contextual typing ideas. It gives rise to a modular design. If you compare this work and the previous work of contextual typing, you can see most of the typing rules are the same. Only the subtyping rules are modified to support polymorphic types. And just like local type inference, it advocates the so-called matching instead of the unification. We will get back to the matching later. It provides clear specification, making it closer to the canonical systems like system F or implicit system F. It removes the practical restrictions of local type inference and offers better locality. It's rigorously studied. Everything has been mechanized in the Agda and rock prover. To our knowledge, we are the first one to mechanize the local type inference algorithms in proof assistance. We hope it can stand as a principled and practical foundations for the inference algorithms and inference languages as a base model for the future researchers. Let's understand how our type inference works. Let's try to use a simple example, but with some hypothetical rules. We wish to apply the ID to the integer one. The ID is, of course, of the polymorphic type in the environment for alpha to alpha. And ideally, this function application has the type integer. So we apply the standard system application rule, which is here. We wish ID to have the type int, and argument have the type int. As you can see, ID has multiple types in the system. How to achieve this, how to achieve a term can have multiple types. Usually, we add a subsumption rule and a subtyping that states this polymorphic type is a subtype of this function type. This is sometimes also called the polymorphic subtyping, and this case is covered by one key rule called the for all left rule in the literature that states that if you have a polymorphic type on the left, you can guess a type C and replace this polymorphic type with its substitution or instantiation in the subtyping derivation. This rule is great. It's very powerful, supports the implicit polymorphism, but unfortunately, the unrestricted for left rule is proved to be undecidable. So people often compromise to a decidable fragment. For example, the predictive type inference algorithms, they restrict the C to be monotypes only. So what's our version of restrictions? How do we achieve a decidable for left rule? Remember, since we are using the contextual typing ideas, this is only the hypothetical rules. Our typing derivation is just slightly different because we have the masks to decorate as the contextual information. We first start with the opaque one, since we know nothing, and then we analyze the argument. We opaque, but argument infers some information. This information will be propagated to the ID, and the function ID is aware of more contextual information, which is blue color int here. Then this information is further being passed to the subtyping and will be utilized by the for left rule. So here's our key insight. We can use the collected contextual information to ensure the guess can be safely met to achieve a decidable system. So here's the complete version of the for left rule in our system. You can spot two different differences between the classical ones. First is we decorated with a mask, which is a function mask, and the super type is a function type, which means in our system, the polymorphic types can only be instantiated to the function types, which exactly matches the key characteristic of local type inference that implicit polymorphism is application triggered only. And the second difference is we have an auxiliary judgment called the instantiability that guarantees us we are able to make the guess. What's the secret of this instantiability? I will illustrate with some slightly complicated example. We use the function f to apply it to three arguments, integer, lambda, and integer again. The f is of the following type in the environment, for alpha, beta, alpha to alpha, beta, and beta as the output type. By using our application rules, because we want to collect more contextual information, we can collect the contextual information for the f, then f, we are able to make the guess for the solution of beta and alpha, and to make the following subtyping holds. So why we can do so? Why instantiability can guarantee we can save to make the guess? You can think of instantiability, it works as occurrence checking, but guided or constrained by the masks in a left-to-right order. The first is a transparent box, which means we know something in the context and we have alpha, so we can save to make the guess for the alpha. The second one is opaque. We see nothing in the context, but we learn this information already. For the previous arguments, we are safe. Next, we repeat again. We have transparent one, we can safely guess the solution for the beta. We do not know information, but we learned this information already from the previous argument. We are safe, everything good. So essentially, instantiability does a left-to-right traversal of the masks and the types in a parallel style. It supports the interleaved inference and checking of arguments because the first argument, whose type is inferred, and we check the second argument, third is inferred again. Great, so far we have a good specification. Let's move towards algorithm because we guess the type is not computed. We introduce a so-called the intermediate system called the matching subtyping that based on one key idea called the matching variables to track the solved instantiations. So we write our for left rule in this way instead of performing the substitution directly on the type A. We store it in the newly created environment delta. And the essence of matching variables is a solution cannot contain other matching variables, which is very different from unification because alpha equal to beta is strictly disallowed in matching. And we can have a very strong invariant, that is, matching variables can only appear on one side of subtyping. Not surprisingly, this is also implied by the original local type inference work. You can spot this premise. It gets a list of solutions, which is A over line, and it only performed substitution on one side is essentially the same with our invariant. Great. The second step to move towards the algorithm is we incorporate so-called the input and output environment because we still do not describe the computation process, how the solution is computed. We introduce the unsolved matching variable alpha. So when we have the for all left rule, then we just put the unsolved one in the alpha. Then we learn later, and we got some solutions in the output environment. You can see the sigma here, which is a little bit scary, but it comes from the idea of the contextual typing that sigma, remember, sigma stores the arguments, and we deal with it later. Essentially, how do we deal with the arguments? We can have two situations. If the information is not enough, we then try to infer. We use open to say this is not enough. We infer the argument, and we learn more information, and we use this information to further refine everything in the environment. Once the information is enough, we then try to check the arguments. As you can see, this process is essentially the same to the instantiability I illustrated in the before because they all follow the left to right order, but instantiability explores the masks. Here, we explore the context. Let's try to run a simple derivation tree to get a big picture how the information flows in the algorithm. Here we use the opaque one to mean the empty environment, empty context, and we wish to infer the ID applied to the one. We do nothing, but only prepend this argument to the context of the ID. The ID is of the following polymorphic type. We then try to compare this type with the context. It matches the shape of the for left rule. Then we create alpha, which is unsolved one, and we further analyze everything in the context to learn alpha is bound to the integer, and we also have the refinement of the types, which is further being propagated back as the instantiated type of this polymorphic type. This type is also the type of the ID under such context, and we use the output type, which is the inference result of this function application. Let's recap. I presented three systems. One's a specification on the right corner, and which just use a very simple rule utilizing a properly restricted for left rule. Then we introduced the matching variables to store it in the delta. And then we use the idea from contextual typing, and we designed the algorithm. Also, we incorporated the idea of the input and the output environment. In the end, the three systems are proved to be equivalent. And thanks to our very simple specification, we can be very easy to build a relationship to the implicit system F in the literature by proving soundness and completeness. So let's conclude. We propose the LCTI offering a simple and modular specification of the local type inference. And we introduce matching subtyping that specify the use of matching in constraint solving. And we have concrete systems. We prove the soundness and completeness across 3 systems. Everything is at this GitHub link, including the mechanized proofs, Haskell prototype, and the extended paper. That's all. Thank you. I'm happy to take questions.
Nice work. Does it extend to f-sub, so where you actually have subtyping in the user?
Yeah, exactly. That's our next step. Yeah, so far we are working on system F, which is kind of the core system that can be extended to different directions. But f-sub is definitely the next milestone of the work. Thank you.
Hi, thanks for the talk. The modes you have, they kind of look like moded logic programming, where you can kind of have things that have different direction, like information direction. Do you have any idea if there's a formal connection, or have you tried thinking about it this way?
Yes, we have the masks, right? And the modes is strongly the modes in bidirectional typing is strongly connected to the modes in the logical programming. And since our masks are generalized over the bidirectional typing, so it's basically if in some advanced logical programming they have the advanced modes, I think they are just strongly connected.
Thank you.
Thank you.
Okay, we also have some online questions. So the question is, why is instantiability left to right? Intuitively, it looks like you could infer information from all transparent positions in parallel and then check the opaque positions.
It's mainly due to the first one is efficiency. We just want to do one pass, and we do have some work that works on the got the information at once and then try to deal with it later. But maybe at some we do not sacrifice the efficiency. So that would be a open research questions. So yes, if we refer to the backtracking, we can do so.
I don't think they implied to use backtracking, just to
one pass or two pass,
maybe just one pass and some constraint solving. So that's also connected to something I wanted to ask, like how do you relate this system in terms of expressiveness with things like Haskell, which also do bidirectional typing?
Haskell is bidirectional typing. First, I'm not very familiar with how the bidirectional typing works in the Haskell, but since we are just belong to the local type inference, and we do require some annotations, which makes the algorithm very straightforward, just in this way. But I cannot give a very clear answers now.
Right. So the main advantage is that the declarative specification is very simple, right?
Yes. Yes. True.
Thanks.
Thank you.
Other questions? So there's a second comment on Discord, but I think it's more of a remark than a question. It says, isn't completeness sort of immediate if you can add extra annotations to check everything? How would it fail?
Which completeness?
Yes, completeness if you add extra annotations to check everything. I'm not sure what.
There is it offline. Yeah.
Yes, you can.
Sorry.
Offline. It's fine. Okay.
Thank you.
Thank you again.